Hello, my name is Carl Wüst and today I will be presenting Bitcontracts, a new system that enables the execution of expressive smart contracts on top of legacy cryptocurrencies like Bitcoin. Our system is compatible with a large number of legacy cryptocurrencies, and I will say a bit more about that later, but I will generally use Bitcoin as an example because it is the most prominent blockchain. So let's start with some background on how Bitcoin transactions work. Bitcoin transactions consist of inputs and outputs that essentially act as coins with variable denominations. Outputs can then later be used as inputs in future transactions. For this purpose, the outputs contain a locking script that specifies some spending conditions. Most commonly, the script requires that this future transaction is signed by the private key that corresponds to an address specified in the output. To spend an output, you then need to provide the spending script, which contains the values necessary to satisfy the locking script. These scripts allow for very simple smart contracts, for example, checking a multi-signature. In this example here, spending the new output with this script would require signatures from two keys corresponding to pubkey 1 and pubkey 2. However, the scripting language is not Turing complete, and because of that, it cannot encode an arbitrary business logic. This in contrast to systems like Ethereum, which is usually what people refer to when talking about smart contracts. So usually we expect that a smart contract can encode anything that we want, essentially. Of course, one option if we want to use expressive smart contracts would be to move from legacy cryptocurrencies like Bitcoin to new platforms that are specifically built for this. But these legacy ecosystems have already attracted a significant amount of users, developers, and investments, and that makes it preferable to enhance these systems instead of migrating all of the users and assets to another platform. That brings us to our goal, which is to retrofit expressive smart contracts into legacy blockchains without requiring changes to the protocol of this underlying blockchain. Before we go into the details of Bitcontracts, I want to quickly cover some related work. First, we have Hyperledger Fabric and ACE, which are both systems that are purposefully built to enable contract execution with a high performance. Both of them execute smart contracts in small committees that are not necessarily involved in the consensus mechanism. A quorum of these committees then need to sign the results of a contract execution for them to be accepted. And this is an approach that we also take in Bitcontracts. However, neither of these two solutions can be used to retrofit expressive smart contracts into legacy cryptocurrencies because they both require additional steps after ordering to ensure consistency. So ACE uses an order execute commit model and Fabric uses an execute order validate approach. This is a problem when we want to retrofit this into legacy cryptocurrencies because the ordering in these blockchains already has side effects such as money transfers, for example, which cannot easily be rolled back after this step. For more details on this, I encourage you to read the paper. The third system listed here, FastKitten, has the same goal as our system, but takes a completely different approach. So FastKitten uses a trusted execution environment to execute smart contracts, and it also requires collaterals from participants to prevent misbehavior. With this approach, FastKitten only enables a specific type of smart contract that has a limited lifespan and fixed number of participants. So for example, this can be used for a single online poker game that has participants that are defined in the beginning of the execution of the smart contract and a well-defined ending of the contract. This is in contrast to a system like Ethereum, where a smart contract can have dynamic participants and essentially an arbitrary lifespan. In addition to this, FastKitten is not resilient against the compromise of the trusted execution environment. Now we'll get to our solution, Bitcontracts. Bitcontracts, as mentioned, adds support for expressive smart contracts to existing blockchains using an off-chain execution approach. The trust model that we use is contract specific, which means that for each contract, a set of service providers is chosen when the contract is deployed, and these service providers are then responsible for executing the contract. The results of this contract execution can be committed if they are signed by a quorum of these service providers, and this trust model is similar to ACE and Hyperledger Fabric. If we want to run Bitcontracts on top of an existing blockchain, this blockchain only has to provide 4 simple primitives that are present in most legacy cryptocurrencies. The first property that this underlying blockchain needs to provide is storage of auxiliary data, which is pretty straightforward. Our solution needs this to store data in transaction, we use this to store state updates in transactions. So essentially all of the state representing the smart contract is referenced or stored in these transactions. The second property is multi-party authorization. This means that transactions need to support an option to say something like, we need signatures from 3 out of these 5 keys, and we need this for a quorum-based authentication. Essentially, we use a multi-signature output to function as the kind of main anchor for the contract state. So one multi-signature output or multi-signature account represents the contract. The third property is a property that we call state-dependent transaction validity. And this means that the validity of a transaction can be conditioned on the current state of the blockchain. This may sound a bit complicated, but it's actually a default behavior of many blockchains. For example, a UTXO-based blockchain will reference an output of a previous transaction in every transaction, which makes sure that this previous transaction is the most recent within the whole chain of transactions. And this property is needed to ensure serializability. The last property that the underlying blockchain needs to provide is transaction atomicity for transactions with multiple sources and multiple destinations. And this property is needed to make sure that the smart contract can send and receive funds. As I've mentioned, these properties are provided by most legacy cryptocurrencies. In this table, you can see an overview of which property is provided by which cryptocurrency. The orange circles here mean that the property is not directly provided, but it can be achieved with some additional protocol that will require additional communication. You might also wonder why Ethereum and EOS are listed here, since they already support expressive smart contracts. The reason is that Bitcontracts could also be added on top of such platforms to enable the execution of more computationally complex smart contracts. That's not the main goal of Bitcontracts, but Bitcontracts can also serve this purpose. And this has been one of the goals of some previous work. How does Bitcontracts actually look like? So here you can see our system model. On the left, we have the existing blockchain system that remains unchanged. For example, for Bitcoin and other proof-of-work cryptocurrencies, this includes miners and of course also blockchain clients. And all of these parties are completely agnostic to Bitcontracts, which is simply added on top without any changes to the base system. What we then have in Bitcontracts are Bitcontract clients and service providers who are responsible for executing contracts. As you can see in the drawing here, only the clients need to communicate with the peer-to-peer network, and service providers can actually be stateless, and they don't need to communicate with each other or with any other parties except for the clients. Essentially they can receive all information that they need from the clients, and our protocol ensures the safety of these contract executions even if the client is malicious. This is possible by making use of these 4 basic properties that I've mentioned earlier. Let's look at a transaction in Bitcontracts and how a contract is executed. So here we assume that we have a user Bob who wants to execute a contract for which 3 service providers are responsible, P1, P2, and P3 here. First, the client either updates the state of the contract locally from new transactions appearing on the blockchain. This option he can use if he has already interacted with the contract before, or he fully retrieves the state by going through all state updates, which means going through all transactions to this contract. He also retrieves the most recent transaction involving this contract, and this we will refer to as previous transaction. He then sends this previous transaction, the contract state, the contract code, and his inputs to the contract to the service providers, P1, P2, and P3. And these service providers can check that the previous transaction correctly references the contract code and state, and then execute the contract based on this. After this execution, they then individually but deterministically create a raw transaction that contains state changes resulting from this execution, and that also performs any money transfers that were initiated by the execution. This raw transaction TX, which will be the same at all of the service providers, is then signed by all of these service providers individually, and they send the signature together with the raw transaction to Bob. Once Bob has received signatures from a quorum of these service providers, so enough to fulfill the multi-signature condition, he can assemble the full transaction by attaching all of the signatures and also adding his own signature if he sends funds to the contract or if he uses his funds to pay for blockchain fees. And then he broadcasts this transaction to the peer-to-peer network, where it will be picked up by miners and included in the chain. A contract call can also involve other additional contracts, and you can find details about this in our paper. I'll now show you how these transactions look in a UTXO-based cryptocurrency like Bitcoin. As an example, we'll consider a simple faucet contract that allows withdrawals and top-ups, meaning that any people can send money to the contract or take money out. And the contract, or we assume that the contract also stores the number of withdrawals and top-ups in its state in two variables called withdrawals and top-ups. In the contract creation, Bob creates a full transaction, so there he doesn't need to interact with anyone. He basically uses one of his UTXOs as input to the transaction, and he creates a so-called contract output. This contract output is the representation of the contract and is basically the main output. It stores the contract's funds and references to the contract code and the current contract states, and these references are basically hashes, which makes sure that he cannot send a wrong contract code or a wrong contract state to the service providers. In this example, Bob only wants to send 65 coins to the contract, so he'll receive the rest back in change output, which is shown at the bottom. After the contract output, we have so-called state outputs. We can have multiple of these state outputs, and they collectively store the updates to the contract state, or in this case, because this is the contract deployment, they store the initial state of the contract. And in this example, since we only have two state variables, we only need one state output because the stored state is quite small. Now we assume that Charlie calls the contract to withdraw some funds from the faucet. For this, he runs the protocol that I've described on the last slide with the service providers, which results in the second transaction shown here. The only input to this transaction is the contract output from the previous transaction, which will be consumed in the transaction. The withdraw function sends 5 coins from the contract account to Charlie, which means that the new contract output now has a balance of 60 coins. And the new contract output also still references the same contract code, so still stores a hash of the contract code, and it also stores a hash of the new state, which now has changed because the withdrawals variable was increased by 1, so the value is now 1. This information also needs to be stored, which happens in another state output, but since this is not the first transaction, we don't need to store the full state, but only the state update, in this case, the new value for the withdrawals variable. Bitcontracts ensure safety and liveness for the contracts. So as a safety property, Bitcontracts ensures that we have execution integrity and serializability for all contracts whose trust assumptions are not violated. And this property holds even if contract interacts with an untrusted contract. As a liveness property, we ensure that a non-conflicting transaction submitted by an honest client will be executed and committed. And this property requires an honest quorum for all involved contracts. You can find more details about this in our paper. We implemented a prototype of Bitcontracts, which is compatible with Bitcoin and other cryptocurrencies that use the same transaction format. Our prototype provides a Python API for contract development and allows writing contract code in Python. To evaluate our system, we collected contract execution data from 130,000 blocks of the Ethereum blockchain, from which we then extracted transaction information of the 100 most popular smart contracts. And this resulted in a data set of approximately 10 million contract calls, which we then used to calculate the transaction size of these transactions in Bitcontracts, as well as the on-chain cost in different blockchain systems. As you can see here in these box plots, the cost distribution for Bitcontracts on top of Bitcoin is very similar to the cost distribution of the contract executions in Ethereum, and significantly cheaper if Bitcontracts is used on top of other cryptocurrencies, such as Litecoin or Bitcoin Cash. For a comparison of the transaction size and additional evaluations, please have a look at the paper. To summarize, Bitcontracts enables support for expressive smart contracts on top of legacy blockchains. Bitcontracts only requires the underlying blockchain to provide 4 basic primitives that are supported supported in most legacy cryptocurrencies. And finally, Bitcontracts achieves this with practical transaction sizes and costs comparable to those of state-of-the-art systems like Ethereum. With this, I finish my talk, and I encourage you to read our paper for more details.